Welcome to Chapter 5, Numerical Integration. So in this chapter we will talk about a few numerical methods to approximate integrals. So here is a typical integration problem where you have the integral from a to b of a function f of x. So this is a one-dimensional integration. And basically we will consider a so-called grid. So this is going to be our x points that we will evaluate our function. And since our domain is from a to b for this integration problem here, we will set x0 to be a and the last x will be equal to b. And basically the so-called quadrature formula is an approximation to this original problem in equation 1, and it can be represented as a sum. Well, basically it's a weighted sum, so you can see that we are evaluating our function at these points on the grid denoted by xj's, and these are multiplied by wj's, which are the weights. So if we can find these w's and xj's, then we get ourselves a quadrature formula to approximate the area basically under the curve f of x. So you can see that so the key here is to obtain these weights wj's and the nodes xj's. And once we have that, we have a quadrature formula, which is denoted here by this q of f. So this is an approximation of the integral I of f. So the difference here gives us the truncation error from the quadrature formula. So you can think of equally spaced grid points. So we can denote xj's in terms of the starting value a plus each step we will go by delta x. So this can be represented by j times delta x, and you can see that j from 0 to n, so we get all the values up to this b. So basically if we select such equally spaced grid points, this yields the so-called Newton-Cotes quadrature formulas. So you can think that from what we write here, we imply that actually we are not required to choose equally spaced grid points. However, this is a simpler approach and it is easier to derive the formulas. And as we say here, this is the so-called Newton-Cotes quadrature formulas. So for more general quadratures, we can actually relax the assumption that these delta x to be uniform. So our grid points actually might be not equally spaced from each other. And we can obtain more complex quadrature methods such as the Gaussian quadrature methods and so on. So we can see that if we consider some polynomial approximation, and so this f of x can be approximated by an nth order polynomial, and therefore we can write actually these lj's. So these are the so-called Lagrange polynomials of degree n. And in the next slide we can see that actually these so there's a d of x missing here. And basically instead of f of x dx, so we are approximating with an nth order polynomial. And so the integral, so we have the quadrature denoted in terms of the fj's times the polynomial functions, because this is coming from the property of the Lagrange polynomials. So the key here is to be able to write the Lagrange polynomials, but that's not very complicated. So we can consider first of all the easy example. Suppose that we are approximating our f of x with lines. So that means we will choose this polynomial to be degree n equals to 1. So if we are considering the n equals to 1, so these are actually lines. And in other words, what you are trying to do is, if you have an integral, let's say of some function f of x, and suppose this is a and b. So if your approximating polynomial is just a first order polynomial, then basically you are connecting these lines. So you are writing the equation of the line that connects these points f of a and f of b. So the question is, how can we write the equation of the line that passes through these 2 points? And for n equals to 1, we can do that easily by following this notation here. You can see that easily you can verify if x equals to x0 in this representation. This term will cancel out and you will get that f of 0, right? So you can try that. If x equals to x0, p1 x0, that's going to give you the f0. And similarly, if x equals to x1, p1 x1, that's going to give you f1 as expected. So in other words, we have, by using this representation, we successfully have written the equation of the line that passes through these 2 points A and B, right? So basically, if we follow this approach, this polynomial term, because we can interchange the integral with the summation terms here, and notice that this is how we write the Lagrange polynomials of nth order. And if this is a first order polynomial, then this is what you have here. So you can integrate this actually, and you can obtain these weights. So basically the integral of this linear the line that we have written can be obtained in terms of this area formula. Okay. So we can demonstrate this in a figure. Actually, this will lead us to the trapezoidal. So why? Because you can notice that for each subinterval here that we take, actually we can evaluate our function at these 2 points, and we can draw the line that passes through these 2 points. And notice that in the previous formula, what we get here is actually the area of the trapezoid. Okay, and you can see that once we do this linear interpolation, actually to replace our original f of x, then what happens is we are generating these trapezoids, which are the areas, right? And basically, in order to approximate the integral of f of x, that is the area under the curve, we are using the areas of each trapezoid. So if we write the area of each trapezoid and we can consider the sum over all these intervals, we can get this more general formula here. And you can notice one thing, and looking back again to the 2-point example here, you have the f of 0 and f of 1, and we are dividing it by 2. So you can notice that for all the points in between this A and B, we are counting this function values. So this is actually f of x1, f of x2, all the way to f of x n minus 1. So these are actually counted in these two adjacent or two consecutive trapezoids. So in other words, the coefficient for all the terms in between is going to be 1, but for the first and the last terms, this is going to be 1/2, 1/2. Okay, so this is the logic behind how we get this quadrature formula in order to approximate the area under the curve f of x. Basically, everything is coming from the geometric interpretation here. You can see that we have each of these trapezoids, and if we sum the areas of these trapezoids, we get this general representation.